Okay, it looks like we've got some people here. I'm going to give you my Ken Burns look here, but fortunately, you won't have to look at me for most of the session. What we're going to be doing is going over some of the stuff that we also did in class, and I'm just bringing up my final study guide here. Right as I was going online, my laptop just said, I've just had too much today, and went into a full hard firmware reboot. So there's a couple of ways that we can you can connect here. You can use the group chat over here. You should be able to see that. You should be able to see my group chat to the side. If you can't, you can also text me at 414-899-8269. And I'm going to go ahead and actually share my study guide with you. Once again, that's 414-899-8269 if you need to text it. You can also email me, and I'll try and keep an eye on the email. So I'm going to go ahead and share this. So you should see the CS361 study guide up there. So the purpose of this is, like we did in class, if you were there on Thursday, what I'd like you to do is do a couple of things. One, read through those requirements. They're not particularly long, but I'm having you think about that system, and we'd like to apply some of these topics to that. The stuff that I'll be asking questions about comes out of basically all the stuff we covered in lecture, a lot of the stuff we did in reading, and a little bit from the labs as well. But they'll have to do with all of these topics here. I apologize for my my cold here. So one of the things we want to do is understand what goes on in software engineering, and that's sort of the softball part of this, and also what the elements of the famous 4+1 view of architecture are. And that is of course, the use case in the middle, surrounded by the logical model, the development view, the logical view, the development view, deployment view, and the process view. And the reason that that is important is it's focusing us on different aspects of how we think about the system. The logical view, of course, thinking about what abstractions exist and how they relate in the system. And then we sort of slide over to the development view, and we start to think about, well, if we want this system to behave in a certain fashion in response to events, how do I design something that actually does that? What objects do I have to build, and what classes would those result in? And what kinds of artifacts am I actually going to build? I have to start to think about the work breakdown structure. And when you break down the work, you say, well, there's a bunch of different classes I have to build, and I have to then compile those into an executable, and then maybe I have to build some scripts that move those executables onto a processor someplace and fire them up. So there's a bunch of different things that go on in deployment. The difference between deployment and the process view is going to be that the process view thinks about what activities are going on in the system and are executing independently, so that I might be able to scale the system in a way that allows me to take advantage of parallel processing, allows me to deploy it. So, you might refer back to the deployment view that says, hey, like in our chrono timer, we said, what if we had like 5 display servers, and each of them grabbed results from the chrono timer. And then I could have many more people connecting to those display servers. They might be geographically distributed or load balanced or some way allowing us to have greater processing capability. Then, of course, there is there's basic UML modeling, and you'll want to know the use case diagrams pretty well and class diagrams well, but you'll also want to know the difference between class and object diagrams. That's something that people often have trouble with, that the object diagrams show us the exact objects that are used to construct a system. So they show us the actual structure of the system. Class diagrams show us the logical relationships between types, but not necessarily the structure of the system at some point. It might show structure of data, for example, but not really. If we're thinking about a system based on object models, which we have been doing throughout this class, the object diagram is the one actually capturing the structure. And so a lot of people mix those up because the human mind likes to do that. We love to classify things. And so we'll say, oh, well, all of those white Toyota Camrys out there are all class white Toyota Camry. But there's 5 instances out there that actually comprise the fleet of cars. We talked about communication diagrams as a way of envisioning scenarios. And what are scenarios? Scenarios are instances of use cases, aren't they? They're a given set of interactions between objects that support the behavior of the system, the response to some event that the system experiences. And so that communication diagram says, as I'm doing my design work, what's happening here? Now, at the very top level, you can imagine a communication diagram between actors and the system. Because remember, actors don't see inside the system, although they may know about concepts like accounts at banks and balances and customer numbers and stuff like that. But at the very top level, the actors experience interactions with the system as described by the use cases themselves. So what is the actor expected to do and what is the system expected to do? Inside, we start to think about communication diagrams. We're saying, well, this object talks to this one, and then this one talks to this one, and gets something from that, and then talks to another one. And we start to imagine the scenario unfolding for how a particular response is handled. We talked about component diagrams and as a way of envisioning the notion of a component, which is an independently replaceable and upgradable part to the system. That's the definition that we see in the Fowler paper, and it's a pretty good definition. We saw a slightly different version in the slides, but it's pretty much the same idea that components are independently usable within the component model. So the one we used in the lecture when we talked about components in general was a little bit broader, but and the one in the Fowler paper was a little bit more focused on services in that I could replace them, take one out, put another one in because they had the same interfaces, and I could upgrade that component and it still operates within that environment. So the notion of components focuses on this notion that I can start to construct a system out of individual pieces. It doesn't always have to be at runtime, but they do have to be independently replaceable. So it could be at a source code level, it could be at an executable level, it could be at a whole source service level, like we saw in the large service-oriented architecture example. So you want to know that, and the representations for the interfaces, as we saw when we were doing the directory example in lab, and as we used with the chrono timer, where it had the 2 different interfaces, one for sending results and the other for displaying results. With iterative development, the main things we want to know about is the fact that while we go through the same steps of analysis and design and testing and deployment, they're scrunched up in agile work. We have in agile development, sorry, and we have smaller units of work that we assign on a backlog basis. But you'll find a lot of organizations that have variations on this theme. And so by looking at the canonical parts of this, the independent parts of this, we have a good idea of when we're doing analysis, when we're thinking about design issues, when we're thinking about test plans, and then they may be deployed, you may apply them somewhat differently in different organizations. So here, if we talked about an iteration plan, what's happening in different iterations? In pure Scrum Agile development, you would only do that for each upcoming sprint. But the real world is you don't just hack away at software. You sort of plan out where you're going to retire risk as you're developing the system. So what did we do in our chrono timer system? We retired some early risk by saying, well, it's a race timing system, so we better be able to do at least one kind of race, and we better get time right, because if your timer isn't right, well, not a lot of value to the system. The iterative development concept is the fact that we continue to iterate over the system, continually retiring risk and increasing the functionality of the system. Which brings us to the notion of requirements in general. And we use the use case model as a handy way of enumerating those requirements. So you'll want to know about actors and the use cases. One of the most common problems I've seen this semester with use cases is that people confuse the structure of the system with the interaction with the system. And when people drew use case diagrams, they sort of started out with good intentions with some actors, but then they devolved into class diagrams on the inside saying, oh, this class does this and this class does this. In other words, they were showing the individual classes that were responding to events. With a use case diagram, all we show are ovals saying, this is the reaction of the system here. It's going to be a scenario, a set of scenarios that have the beginning preconditions, and then we talk about their main flow, any exceptional flows, and any alternative flows. And when we talked about the difference between exceptions and alternatives were basically planned changes to the behavior based on conditions. Exceptions were when things went wrong, and they may be recoverable or not recoverable. Okay, so we talked about that a fair amount. So scenarios are instances of use cases. And the reason that's important to remember is it's a handy way of taking a use case and saying, well, let's go down and think about the possible scenarios. And we look exhaustively at the ATM. I bet you'll never go up to an ATM after this class thinking the same thing anymore. But you'll go up and think about what are the different scenarios that can happen for the use case of withdrawing money. Assuming that I do my identification and authentication properly, I'm now in a state where I can do a withdrawal, or I can do a deposit, or I can check my balance. And if I'm doing a withdrawal, I might have a scenario where I take too much money out and it doesn't allow me because I don't have enough money in my account. I'll take it out and there's $20, and I get my $20. I might take it out and there's an exception with the dispensing of the cash. In other words, there's a hardware exception. That's not really an alternative flow. We weren't expecting that to happen, but we do expect the system to recover from that. So we have different types of scenarios, and it's a handy way of enumerating all of those different flows. And we're going to talk about that in a little bit when we talk about method and flow graphs and method coverage and branching coverage later on. We make a fine distinction between functional and non-functional requirements for a couple of reasons. When we focus on functional requirements, we're thinking on the business value of the system. What is the system doing for my user that's of value? In the case of the ATM, it is withdrawing cash or depositing cash into my account. When we looked at the chrono timer, the use cases had some pretty simple values. I wanted to be able to set up a run and then execute runs for each individual racer. Notice that we had this overloaded notion of what a run is. There's the run as a group, and then there's the run for the individual racer. You see that a lot in requirements modeling, where you'll have overloaded words. The same word means different things in different contexts. So the functional behavior is describing what the system does for the user. What value does it deliver? The non-functional requirements constrain that behavior in some fashion. Now, there isn't always a non-functional requirement, but typically as systems grow, we place non-functional requirements on the system that are either global, such as, well, all transactions must complete within 1 second or error out, or we might have very specific ones. That when a racer trips a trigger, the time must be recognized within X number of milliseconds of the event of the racer actually tripping the device physically. Well, that's it's a pretty detailed requirement, but it's not really a functional requirement. It doesn't change the logical behavior of the system or the value it provides, but it does constrain its behavior. So typically, it's going to constrain the performance of the system. In other words, how fast something happens, how reliably something happens. The scalability, it must be able to support 100 users. It doesn't really add any additional, it's not doing anything of value for each use case, but it does allow more people to do it. It might be platforms or external components. In other words, you must use this component. You might say all of them must use Java 1.8 or 1.9, or maybe they exclude things, cannot use a certain platform. So the reason that we have all these requirements is we want to make sure we meet the required behavior that the user is expecting. What value are they trying to get out of the system? One of the hardest parts about requirements modeling is that you usually don't have them all. And by asking about each of these requirements, we start to understand what the boundaries are of them. What are the boundary values? We might say, well, if a racer never finishes a race, what's the finish time? And we said, it's a did not finish, because they didn't take a really long time. They just never finished, right? So that's important to be able to ask additional questions. Just checking to see if there's any questions here. And, oh, good. And so what that does is it leads us into the notion of testing. And tests, there's basically, you should be able to think of tests for each requirement for two reasons. One, if you can't test it, you'll never know if you delivered it. And two, if you can't write a test for it, is it really a requirement? In other words, if you have a requirement that said the system should run as fast as possible, like within nanoseconds or within microseconds, and so what you would do is you'd say, well, how fast does it need to run? 2 seconds, 3 seconds? If somebody says, well, every transaction should finish within at least 2 seconds, at most 2 seconds. You go, okay, I can do that. I'm going to ask you for another non-functional requirement, or maybe I go back and say, what's the business value of that? Because it's going to cost me a lot of money to do it in 2 seconds. I can do it in 4 for a lot less money. Is there truly, or were you just making that number up? Or is this truly a requirement, or were you just making that number up? So what that does is it causes us to start to think about boundary values and saying, well, how can I break this? You know, what are the true bounds of this test? And what's the required behavior if I go beyond those bounds? In other words, what happens if I divide by 0? Or in the case of the chronotimer, we had a very explicit requirement that said the bib numbers could be between 0 and 9999, 4 nines, as I believe it was. A lot of people didn't test for that. And so what's the exception at the end of that? So a lot of times when you're writing the tests, you wind up going back and modifying the specifics of a requirement by saying, well, this is my interpretation of it. Do you believe that to be true, Mr. Customer? And then we also think about stress testing, which is trying to push things well beyond the bounds and seeing how well the system recovers from it. Black box testing, we saw, is where we tend to know the input values, and it also tends to be at higher levels in the system. We don't know what the system's actually doing on the inside. And at the very highest levels, we have the acceptance test, which is whether the customer executes all of the acceptance tests and say, if it passes these tests, then yes, I certify this as being complete. Passes all the requirements that I believe that I'm willing to test. And you'll see this when the Navy gets a ship delivered to it, takes it out for sea trials, and it's basically running down its requirements list. Can the ship turn a certain number of degrees in a certain period of time without tipping over or listing too much? Can it go at the maximum speed? Can it stop within a certain distance without causing damage to the system? All sorts of stuff like that. So that kind of stress testing tends to go on at slightly higher levels. White box testing, as you'll recall, is where we have intimate knowledge of the inside of the system, and we methodically attempt to test the limits of that system, because we don't always know how that component or that unit of software is going to be used. So in white box testing, you'll want to know basis path calculation, like we talked about, and understanding a flow graph, so you can say, how many different branches are going to occur in this? And one of the things you're going to find is that the number of branches, especially nested branches, will increase the basis path result pretty quickly. And every time you do that, you're introducing new testing complexity to the system, risk of failure, additional cost, etc. There's actually schools of thought that say you should have at the most one branch in a method. That, if you have more than that, things are too complicated. So when we look at individual objects, for example, a class of objects, and we look at the methods that the object defines, and we look at each and all of the methods, in other words, the set of methods it defines, and then within a method, the making sure that we cover all of the statements in it, which by definition also make sure that we handle all the branches. We want to be able to take all the branches and make sure that we've executed all the statements. A lot of runtime environments will do this for you automatically now, or the compilers will at least predict, hey, this statement's never going to get executed. Do you really mean that? Method coverage is not the inside of the method, but making sure that each of the methods of the class is tested and tested in the appropriate order, so that you don't have any exceptions to state handling. One of the things we do when we do our analysis is we're really thinking about the domain. In other words, we're thinking about the problem from the user's perspective, from the domain's perspective. And so if we're thinking about banking, we're thinking about things like accounts and balances and withdrawals and deposits, and lots of different things having to do with banking. But we're not thinking about lists and queues, although we use the word queue as a business processing concept, which is first in, first out. But we also have the notion, of course, of queues and data structures. But those are just sort of overlaps because we stole the notion of a queue to use in data structures. But they are typically, in the domain model, we rarely involve any sort of design level activities, if at all. You shouldn't involve any. The design activities that we then go through, we say, what would be the best way to build an object that behaves the way we want it to behave in our solution domain? So the domain model says, this is all about banking. And then we turn around and we say, well, you know what we're going to do? To handle routine teller transactions, we are going to have an automated teller machine. We even throw the automated part in and teller. So we're saying, well, we're automating the teller activities. We're not automating loan activities. We're not automating a lot of others. So we carve out a specific part of the problem domain and say, this is the part that I want to model in software, and I want it to behave as if it were a teller. It's going to fulfill all of the goals of a interaction with a teller, and we're going to model it in our software. So we start to drill down and say, well, how can I actually build an object that would do these things for me? And that's where we start to invoke the notion of design patterns. For example, we used command pattern a lot in the chronotimer because we saw that the chronotimer was going to respond to a number of different events, and it turned out to be a handy way of describing the system. Let's see. I just want to make sure we don't have any questions. Okay. We looked at the memento pattern, which is a way of saving the state of an object in sufficient detail that we could reconstruct that object back to its original state in another instance of the program. We, of course, talked about the model view controller, one of the most famous patterns. And I'm just going to yep, okay. And with the model view controller, we saw the separation of concerns where the model was primarily responsible for data, the view primarily responsible for representation of the model, and the controller primarily responsible for responding to events from outside and determining the semantic activity. You know, how does that change the model? And we actually saw how HTML and CSS work together in this respect, where HTML was largely responsible for structuring data, and CSS, the cascading style sheets, was primarily responsible for describing its appearance. And so we talked a little bit about the history of that and why HTML got a little overloaded. Then we said, hey, let's just break this up into, here's stuff that's largely representation independent. Here's stuff that is in structural. In other words, here's the structure of the data. For example, we had race results, and the race results had things, each of the individual racers and their times. And you'll find that the HTML, boy, that's not a surprise, looks a lot like the definition of the classes themselves. And in fact, we saw a sort of implementation of persistency in JSON where we said, you know what, we're going to take each of the fields in an object, each of the data, and we're going to perhaps recursively describe the data that's in that field. So if we had a simple object, such as a person with a name and an age, where the name is just a simple string and the age is an integer, our JSON said, well, the name has this string associated with it, and the age has this integer associated with it. If it was a more complex object, for example, if the person had an address associated with it, and the address itself was a complex object, then we could recursively embed that JSON in there. So JSON was a way of creating a environment independent way of describing name value pairs for persistency. Then we also saw the publish and subscribe and observer pattern. You'll want to know how that works. And the fact that the model view controller actually uses the publish subscribe as a way of saying, if a model has multiple views, well, the model is the observed thing and the views are the observer. And so if the model changes, the views can update. We also saw the facade pattern, our famous compiler example, but the facade is a way of using a single object to represent the interface to a more complex system of objects underneath it. Persistency, we mainly focused on the notion that certain entity style objects, excuse me, I need to cough. Certain entity objects, and when we say entity, we meant these are objects that tend to represent things that are kind of static. They don't do much other than sort of remember stuff. They remember sort of the semantic model of the system, but they aren't particularly active. And those tend to be persistent too. So, for example, in the spring midterm, when we talked about parking spots and cars and stuff like that, we saw that the parking system had an inventory of parking spots, and that it could rent out. And that inventory was sort of a bunch of entity objects. There isn't much. Parking spots don't do much. We know that they have a number and a location and a rate, but it's largely declarative data about that. And so from a persistency perspective, there's a couple of ways that we can do it. We can say, hey, class, give me yourself as JSON, or we can do it as we did it with JSON in the example there. It knows enough to go ask the class, hey, what fields do you have, and what are their types? And then I'll generate the JSON for you. So the class never has to know about that. We call that a factory. And then we also have the ability to say, hey, this class, each of those variables in there maps to a field or a column in a database record. You don't need to know how that works, but that's in there. And then finally, we had a fair discussion on software architecture, and you'll want to know coupling and cohesion, and you'll want to know the notion of layering versus partitioning. Under interfaces and protocols, we talked quite a bit about designing to interfaces and not to implementation. In other words, think about the interface to the object and make sure that your design assumes the interface and not an implementation. We also talked about the value of extending interfaces rather than changing them. And what that does is it reduces the coupling in the system, and it also makes it a lot easier to make changes because you're not changing an existing interface and therefore breaking a bunch of others. You can always add in new capabilities. And we saw the example with the multiple FTP class. We talked about the JSON and the CSS there. State and state machines, the only thing you really need to know here is what a state diagram looks like in UML and what the purpose of a state machine is, that it defines the transitions from one state to another based on the response to an event, and that transition may be conditionally affected by guards. And so that's about all you need to know. If you remember the garage door example and you can sort of look through that and say, yeah, I fully understand the garage door example, then you'll be good. Threads, you really just need to know what happens when we have, we start up a thread and then we can join them together and then the relationship between a thread and a process in Java. I think that's pretty straightforward. Change management and configuration management and version control, you can sort of roll together, and that is that we're thinking about what items are going to be built, which build requires a particular item, and which version of it. And then a version is the evolution of a configured item over time. And so you'll notice that there's no restrictions on how much a item can change. I could take out all of the source code and put in all new source code in a configured item, and it's still the same configured item. It's just a dramatically different version of it. But there's, so we have the notion of version control and configuration management. So you'll want to sort of know that distinction. And then there's the process of change management, which says which items have to change if I change a use case, which configured items have to change, and which versions am I going to create. And we saw that we can have smaller and smaller versions and continuously rebuild the component and redeploy it, although that cost goes up. Finally, you'll want to know the definition of a component and the notion of a service and a microservice and where they live in the 4+1 view. And the notion of the interfaces as they're required, because they're really important to be able to both identify the interface, discover it, and then, of course, you are building to that interface, not to the component behind it. We're not going to have any questions on the economics of reuse, so you don't have to worry about it. When we talk about messaging between components, we're just interested in the fact that we may have things that are relatively lightweight but not terribly reliable, or we may have things that are very reliable but kind of heavy. So those are the things that I think you can expect to see on this. Certainly can't guarantee every one of them, but if you have a reasonable command of those things, then you will have done well in this class, and you'll be able to apply it to a lot of different scenarios in your professional development. So I think this class covers a lot of great concepts that are immediately applicable in a professional environment. And I think you'll find that the text is a good reference as well. It's one of the reasons I sort of use that as my backstop is if I'm going to have somebody buy a text, I want to make sure that it's one that they can use over time. I haven't gotten any questions either by text or email, so I'm just assuming that everything was crystal clear. If not, feel free to email me tonight or tomorrow. Just to refresh our memory that the exam is at 7:30 on Thursday morning. I actually had somebody stop me at the building the other day, and they were surprised to learn that in fact it was at 7:30. They thought it was later in the day. So it is in the same room that we're in. You should bring a pencil, a good old number 2 pencil that you're used to using. And let's see, let me stop sharing my screen here. So a good old number 2 pencil, or maybe 2 of them. And on your exam, you'll have the questions, and then you'll have some sheets with figures on them. That way you can sort of see the figures a little more easily. And So some of the questions may refer to those figures, and then there will be a single blank scratch sheet if you need it, and all of those will be stapled together, and you'll have to turn that back in when you're done. You'll also have your answer sheet, which will be the actual Scantron sheet, where that's the only place where you would supply the official answers. And so on D2L, you should see most of the stuff is graded. I think there's maybe a lab or two here and there, and a little bit of Sprint 4 still left for one or two groups. But for the most part, if you see something that doesn't have a grade in it, and you think you submitted something for it, be sure to let me or your TA, start with your TA, make sure your TA knows that, and you can copy me. If you haven't taken the quizzes by now, then you'll have zeros in those. Any labs you didn't turn in, we'll be putting zeros in those. And then as soon as the final exam is graded, we'll put that in, do a little last QA, and the grades are due out by the 24th. We usually get them out sooner than that, but that's the official time they're due out. If there aren't any other questions, I think that should give you enough work. I really enjoyed teaching the class this semester, and I've enjoyed my association with the university. Good luck, and we'll see you for a little bit on Thursday morning, and have a good summer if I don't talk to you there.